My name's David Hollman. I work at Sandia National Labs on parallel and concurrent programming models for high-performance computing. And I'm going to talk today about how to use concept-driven design to fight implicit interfaces, fight against use of implicit interfaces in your types and in your concepts and in your libraries. So you should be able to follow along with my talk, dsh.fyi/CppCon-2019. There's a QR code there if you want to. Apologies if it doesn't look good on your screen. Please judge me on my C++, not my CSS. Okay, so outline of this talk. I'll introduce some material. I'll talk briefly about Hyrum's law. It's been all over this conference in a number of different great talks, so I don't need to talk too much about it. I'm going to talk about the specific scenario where you can fight it with this particular tool. I'll talk briefly about concept-driven design in general, although I don't think I really have to say much because Sean Parent just 2-3 hours ago gave one of the best talks on concept-driven design I've ever seen. Not one of the single best. Like if you're on YouTube and you haven't seen it yet, stop watching me, you're wasting your time. Then I'll go through and talk about breaking things by example. I only have 30 minutes, so I only have a couple of examples. But I'll go through a contrived example a little bit. It's kind of way oversimplified about containers. And then I'll go through a real-world example that I'll try and kind of hand wave through as many of the details as possible to get to the actual real-world example of this kind of effect out in the wild and how we're addressing it. And I have a live demo, and if at any point during the talk I'm talking too quickly, I apologize. I really want to get to this live demo. My team has worked really hard on putting this together, and I want to make sure they get the credit. So apologies if I'm going a little too fast. It's because I want to make sure I get the live demo in. And I'll conclude. All right, introduction. So Hyrum's law. There have been several great talks on this this week already. I'll recommend Matt Kulakundis' talk on Google's hash map, flat hash map thing, and the issues they had there. And Titus's talk this week also goes through a lot of the real-world issues that Google's had with Hyrum's law. Hyrum's law is that basically, if you have implicit threads sticking out of your interface, people will use them. People will pull on them. If you have loose ends that are implicit to your interface, people will abuse them. The main argument of this talk, and I think probably a logical follow-on to Hyrum's law, is that basically you should just be aware of this. And when you're designing your interface and you're faced with the possibility of exposing implicit behaviors in your system, you should make sure that code that could be dependent on those implicit behaviors doesn't accidentally work, or do so as much as possible. And when we're talking about concept-driven design, we actually have, when we're exposing our library in terms of concepts, we actually have some tools that we don't really have in concrete type land. And that's what I want to talk about today. So I'm talking about a specific scenario that comes up probably more than you think, or more than it sounds. It's a library-client relationship where the library provides an interface in terms of concepts and also provides a set of models for that concept. So when I say models for the concept, for those unfamiliar with the language, it means types that meet the requirements of a concept, right? So a library may provide an interface in terms of concepts and some models for those concepts, and it expects the users, their immediate clients at least, to write code that's generic over those concepts. And you want to reduce your client's reliance on implicit behavior that might arise across maybe a subset of those models that are part of the contract of the model itself, but not necessarily part of the contract of the concept itself. And then the client often is somewhere in the middle of the stack, right? Usually has someone writing code to them, not always, but and they need to write code that's generic over these concepts, and users of their code will provide whatever concrete model often that needs to be used with their algorithms, and their algorithms need to obey the generic contracts for these concepts because their users could be passing them a specific model that may have different properties from others. And they need a way to write tests that enforce this kind of thing. So I'm going to breeze through concept-driven design in general because Sean Parent gave, again, the greatest talk on concept-driven design I've ever seen this morning. So, but concept-driven design is not new. And if you watch that talk, you will see why. It's been around for over 20 years. In fact, concept-driven design is generic programming. That's the key to this whole discussion. I'm actually not even going to use C++20 concepts light notation in this talk to further drive home the point that concepts are just a thing that arise out of the way we use templates and the way we express interfaces in terms of templates. Concepts light from C++20 gives us a way to check a very small portion of that and to interact with a very small portion of that, but concept-driven design is a much broader topic. And again, go watch Sean Parent's talk. Why are you listening to me? So concept-driven design arises from algorithms. You look at the way your generic algorithms are using the templates, and you coalesce around a set of constraints and a set of axioms or semantic requirements of a given concept that kind of minimizes the difference between flexibility and cognitive load on the user. And so a great paper about this, Andrew Sutton and Bjarne Strustrup in 2011 basically go through the design of how concepts should be designed under these two different design criteria. Also go watch Sean Parent's talk. So yeah, the key point is concepts light are a language feature that lacks a way to describe most of the requirements of a concept. Concepts are not just a set of compile time requirements, and in fact, most violations of implicit interface issues surrounding concepts have to do with their semantics and not with their syntactic constraints. So, all right, let me try and briefly explain what I mean by breaking things. Probably the easiest way to start is with this contrived example involving containers. So, can anyone tell me what's wrong with this code? I'm going to take a drink. But I bet half the people in the room have seen this bug before.
Is that reference language?
Yes, you've invalidated a begin iterator. So, because you call pushback, pushback, according to the contract of the container concept, right? Pushback is allowed to invalidate any iterators and any references to elements. This is the way the standard at least describes pushback in its constraints. It's possible that the begin iterator for this range-based for loop will be invalid halfway through. You'll get a bunch of garbage in your values that are moved from, and your code will display unusual behavior. But the problem is that this accidentally works for stdlist and stddeck, and often it accidentally works for stdvector, because maybe all of your test cases, your unary predicate only matches one or two items, and your vector doesn't happen to be close enough to capacity in all of your test cases. So the problem with this example, and this is kind of a contrived and simple example, but is that the code accidentally works and could be working in production for many years before you find out that you violated or used an implicit portion of the interface. So we have this process to try and break to provide a breaking model for the concept where we identify what went wrong and or what's accidentally working, and construct a model that stresses that behavior, that exemplifies the extremities. So in this case, it's really pretty simple. The user has assumed that the begin iterator is still valid after a call to pushback. Okay, so what can we do? Well, we could provide a test model for container that invalidates its iterators every time pushback is called, right? Everyone in this room probably who's written C++ before can imagine what that would look like. You maybe allocate 2 buffers instead of 1 and swap all the elements over and then swap them all back every time you call pushback, or swap them into a new memory location. All kinds of fancy things you can do. There's probably a lot better ways of doing that. So I'm not going to go into details, but the point is that you should consider doing it, right? Because your users need to be able to run these sorts of tests. So what are we looking for precisely when we're looking at breaking things and things that are implicit in a model of a contract? So Titus gave this great talk. Again, go watch that. Come back and watch me maybe, or watch more of his talks or something, because he's better at this than me. But he had a great talk earlier this week about code changes at Google. And so he talked about a couple, particularly for functions, he talked about a couple of things that I thought were pretty relevant here. He talked about how for a function, it is possible to make a change that weakens preconditions and strengthens postconditions. But it's essentially impossible to make a change that strengthens preconditions and weakens postconditions, because you're actually going to break a fair amount of people's code when you do that. And it's going to be breaks in semantics and not necessarily in syntax, and those things are going to be very hard to detect. So applying this lesson to models of contracts, you're actually going to end up with something that's backwards here, and I'll explain why in a second. Is you want to look for models that accidentally weaken preconditions of your algorithms or accidentally strengthen postconditions of your algorithms. And the reason for that is that when the user is then given a different model of that concept, that quote-unquote change, which isn't really a change in the code, but is a change in their test or a change in their use case, will strengthen preconditions or weaken postconditions, which leads you to the second case up here of the impossible changes. And that'll lead to chaos, or I say or worse, because you may just end up being forced to change the contract of your concept to something that is less ideal for your use case. And we've seen that a couple of times at Sandia with these kinds of problems. So let's jump into the real world use case. Part that largely motivated this talk. I'm going to give a really whirlwind background of how Kokkos works. I don't expect everyone to completely understand it. It takes us 2 to 3 days to train people how to use the full depths of Kokkos, but hopefully you'll get some idea of at least what's going on in these examples. So Kokkos has these 2 concepts that are the basis of all of our portability, performance portability that we are trying to provide to our users. Our users need to run on a massive amount of different kinds of hardware with different processors, different memory spaces. And so we abstract these things using a generic concept for execution space and a generic concept for memory space. And the execution space, models for the execution space are things like the GPU or the CPU. You could have a NIC that has the ability to execute code on it. You could have processor and memory instructions. Those are kinds of things that we would represent as models of execution spaces. And models of memory spaces could be main memory, could be non-volatile memory, could be programmable cache or programmable scratch pads, could be GPU memory. And so our users are supposed to write code that is generic over these 2 concepts, and there's some things inherent to how they interact that really allows their code to run anywhere in any way that they need to. So the rest of the design of Kokkos involves, well, a large part of the rest of the design of Kokkos. There's a lot more, but involves this kind of primary parallelism motif for launching kernels. So there's a parallel pattern. In this case, it's parallel 4. There's an execution policy that kind of tells how and where you're going to execute that pattern. And then there's some user functor, parallel functor, that describes the actual work. And so the parallel patterns in Kokkos are all they're all asynchronous. The user has to explicitly introduce a Kokkos fence in order to a call to Kokkos fence in order to guarantee that the parallel for or parallel reduce or parallel scan has completed or even started. And so you can already see where people may be accidentally taking advantage of certain implicit portions of that. So here's a quick example that's broken in several ways. The basic idea here, though, is that we're creating a 100 by 200 array named data. I'm terribly sorry for the fact that we have an owning thing named view. We were pretty bad at naming things, and we were young and naive, and I'm sorry. And we're using it with this parallel pattern named parallel 4 on the execution policy named MD range policy, which is parameterized on the execution space. The construction of the data is parameterized in the memory space, right? And then we're iterating through this multidimensional range policy with I from 0 to 100 and j from 0 to 200. And then we're just doing something stupid like storing the product of I and j in I comma j. And then the user is trying to do something they're not allowed to do for multiple reasons. Assert that 6, 7 equals 42, right? Which should be the case if you were accessing the memory correctly or at the right time, because 6 times 7 equals 42. But this code is broken, but it accidentally works. And that's a problem, right? So if we give it the OpenMP execution space or and the host memory space, right? So the host memory space is implicitly accessible from the implicit host execution space, and so this just works, right? And the OpenMP execution space is blocking because of the properties of how OpenMP works. And so it just happens that this kernel finishes before this assert and that this memory is accessible. And this is a problem for multiple reasons, because people usually write their code closest to how it was written before when they migrate to Kokkos. And the first step is usually to do something on the CPU, some CPU version of the algorithm, and use some CPU memory space and some CPU execution space, and things just work. And so, like for maybe 100,000 line code or so, or 200,000 line code, the porting process to Kokkos might take, say, 3 months. And the idea is that they should be able to, the process should be able to then go from that 3 months to the GPU in just 1 day. You just swap out all of your models for execution space and memory space to be GPU ones. But the problem is that people are using implicit parts of the CPU execution and memory spaces, and that ends up just not working. So you can see in the case of the CUDA execution space and the CUDA unified virtual memory space, well, this is unified virtual memory. This is still accessible from the host, but the CUDA execution space is asynchronous, and there's no fence here. And so we'll just have the assertion fail. And then worse, if we use the explicit CUDA space rather than the CUDA UVM space, this memory won't be accessible at all, and we'll just get a seg fault. So here's a fixed-ish example to get you an idea of what kinds of things you would need to do to make this generic. So we would, first of all, want to make sure that the execution space and memory space, the memory space is accessible from the execution space, so that the kernel here will have access to the data inside of the kernel. We would, after the kernel, if the if the memory space is accessible from the host, then we can just fence and do our assertion on the host. Otherwise, we need to do something to ensure that the memory is accessible inside of the assert. So one cheesy way to do that would be to make a range of 0 to 1 and run our assert there. And then fence. So let's talk about this real world use case. How should we break the execution space so that the code breaks before they go to the more complicated model of the concept? So there's a couple of assumptions the user could be making. The more common one is that the user is assuming the parallel kernel is executing earlier or finishing earlier than it's required to. And this is, again, largely because both the serial and OpenMP memory spaces run all of the kernel in a blocking manner. And so logically, we should probably provide some model of CPU execution space that waits until the Kokkos fence is called to run anything. And the opposite extreme, we don't come across this very often, but could certainly be the case, is that they're assuming the kernel is executing later than it's required to, in which case you want one that executes in place, like the serial or OpenMP execution space. Breaking the memory space is a little bit more complicated, and that's where our live demo is going to come in. So there's several assumptions the user could be making. The easiest ones to solve surround cases where the user is using our memory model correctly. They are actually working within our data model, sorry, not memory model, our data model. They're accessing everything using the Kokkos view abstraction, but they're not accessing it from the correct execution space. So either they're using the wrong execution space with the wrong memory space inside of a parallel kernel, or they're using a memory space that's not accessible outside of the kernel from the host. And so we want to provide a memory space, a model for memory space that poisons memory when it's not supposed to be accessible. And that's what our live demo is going to show. There's also the case where the user's not correctly using our data model and they're accessing data that's not through a Kokkos view. And that one's a little more complicated, and we're working on this right now, but that in general requires some sort of compiler support, because this could be accessing an address that's on the stack. They could be accessing an address that's allocated by some mechanism we don't control, and we'd have to go in and find those accesses and mark them as poisoned in the right places. So live demo. Thanks a lot to David Polyakov for putting this together. He really came to my rescue when certain things weren't working, and yeah, I just wanted to call out to him there. All right, so here's our example from the slides, slightly modified. I've added in the Kokkos fence here, since we're mostly going to talk about just the breaking model for the memory space. Assume that the user's already used our breaking model for the execution space and found out that, oh, hey, I'm not waiting in the right places. So, if we have this as is, and this is where most of our users start, is the serial execution space and the host memory space, then this should just work, hopefully. Yeah, so we get my function ran to completion with no problems, right? And that's because this memory is on the host, and our execution space can access that, and so both of these memory accesses are valid. It's also blocking and all of those kinds of things. But we want to break this, and so David Polyakov has been working on this Kokkos logical memory space that it takes a name for the debugger to display, and it takes a memory space that it should be using for the actual allocation. So it still has to use the memory somewhere. It's just going to fake whether or not it's accessible or inaccessible. So I'm going to give this a name. I'm I'm going to name it CUDA sim, right? Because we're going to simulate if we were running on the CUDA memory space. And that should be it, right? We need something that's, if we're going to go about doing this, you need something that's non-intrusive. People won't use it if it's not non-intrusive. If they have to go in and change their algorithm, they won't use it. And so, with any luck, I should be able to make this. I need to load his sanitizer library through an environment variable. This is how you load profiling libraries in Kokkos, and we're kind of abusing the profiling interface in Kokkos to make this work. And we get some output where we've poisoned the host and poisoned CUDA sim for the time that it's not accessible. And we run our kernel, we unpoison it, poison it again, unpoison it to run the kernel, poison it again at the end, and we get our failure at line 20, which is really helpful because line 20 is the place where we violated the contract of our memory space. So yeah, thanks to David for putting that together. And the point of that is that you may have to think pretty creatively about ways to construct models that break user code. But when your code gets sufficiently large, your user base gets sufficiently large, it'll be worth it. So again, I want to reiterate this. Even if you're not used to concept-driven design, even if you're not using concept-driven design, keep in mind ways that you can make your user's code not accidentally work. And also watch Sean Parent's talk. So questions?
So the space poisoning thing you have, which is really awesome, by the way, it looks really cool, requires your clients to augment their tests in some way. Have you considered just having your default policies be meaner in debug mode?
A lot of our users use debug mode. This is very slow, first of all. So probably they would run out of memory in debug mode in many cases, making this useless. A lot of our users do in tests or gold tests rather than unit tests, which is a problem. Oh, we do both. Yeah, that's true. Our well-behaved users like Mark do both. That is true. But yeah, so those tests wouldn't work. The other thing is that,
or just having compiler options so that they can turn on without rewriting their tests.
Yes. So yeah, basically that. A lot of our users write their tests generically, the good ones at least, write their tests generically over execution space and memory space anyway. So they could do this with a compiler flag very easily.
Thank you so much. First of all, the question is whether you considered to make the default execution policy to synchronize things. So just by default, unless a user specified that this particular execution is asynchronous.
So no, it's actually, we wanted to go the other way around, right? Because synchrony has a high performance cost with GPU backends, right? And so if our users are synchronous by default, right, they're going to pay a significant performance cost when they go onto the GPU. That's actually pretty unreasonable for them to be paying. And so we want them to write code that is asynchronous by default. That said, a number of our code bases have trouble with this, and we have options to make things synchronous by default in our build system.
Thank you.
All right, thanks everyone. Thanks for coming.